So I want to talk about just arithmetic with radicals today. So we'll talk about adding and subtracting expressions with radicals, multiplying expressions with radicals, and we'll at least start to dive into rationalizing denominators. So this really represents 2 assignments worth. This stuff is going to be H.8.4 practice, and this one, I think that's the H.8.5 practice. Okay. And so if we don't all get all the way through the rationalizing denominator stuff today, we'll do a little bit on Monday, but you should have good amount of work time built in on Monday too. Okay, so when we're adding and subtracting radicals, it's the same concept that it was when we were adding and subtracting terms, like in a polynomial, for example, right? We can only add like terms, and what determines if they're like terms? At the time we were talking about polynomials, and so it was the variable, which included both the type of variable, was it an x or a y, and the power of the variable, right? So with radicals, it's the radical that determines if these terms can be added up, these radical terms. So we'd have to have like radicals. What would that encompass? What things would have to be true for radicals to be like radicals? What's one thing that would probably have to be true? Same kind of root. So the index would have to be the same. It'd have to both be square roots or both be cube roots or something like that. And what else would have to be the case? The radicand would have to be the same also, yeah. So 3 times the square root of 5 plus 6 times the square root of 5, well, those are both square roots of 5, so I can combine them into 9 times the square root of 5. And if you want to think about the intermediate algebra step, what is the common factor in those 2 terms? It's the radical. So I could factor that out, and what would be left behind? 3 plus 6, right? You don't probably have to think about it that way in your head, but that's technically what you're doing. These would be unlike radicals, because even though the radicands are the same, the index, I have an index of 2 and an index of 3. The indices are not the same, right? So we could not combine those. So let's get a little practice. What's the top one? 8 times the square root of 3, I agree. What's the second one? Everybody? 6 square roots of 2, good. Next one? Can't do anything, right? That one is, can't simplify, they're not like radicals. Bottom one? Can't simplify again. Not like radicals. Oops. There we go. Okay, what about A? Can I combine those? Doesn't look like it, but are you sure? Maybe, right? What could I do to see? Yeah, I could simplify each radical first, and then it's possible that I would be able to combine them. So how would I simplify the square root of 20? What's the biggest perfect square factor of 20? 4, right? 4 times 5. Okay, and I picked 4 because it's a perfect square. What's the biggest perfect square factor of 45? Biggest perfect square that divides into 45? 9, right? So I could do that. I could split this one up into a square root of 4 times square root of 5, square root of 9 times square root of 5. That's going to give me a 2 outside the radical in the first case and a 3 outside the radical in the second case. Okay, and then look what I get. I get 2 radical 5 plus 2 times 3 is 6 radical 5. So what's my answer? 8 radical 5. Okay, so what's the moral of the story? Well, if you're trying to combine terms that have radicals, what do you have to do first? I have to simplify the radicals, right? Because I don't know if I can combine them until they're simplified. Okay? How about this guy? Now I've got cubes. So if I'm shifting my thinking a little bit. Instead of trying to find the biggest perfect square factor of 54, what am I trying to find here? Perfect cube factor, right? So what is the biggest perfect cube factor of 54? In other words, the biggest perfect cube that divides evenly into 54. There's a list up there of perfect cubes. 27. Yeah, right? 27. How about 16? What's the biggest perfect cube factor of 16? 8. And then 2 is obviously prime, right? Okay, so we get something like that, don't we? Cube root of 27 is 3. Cube root of 8 is 2, right? So then what do we get? I get 3 times the cube root of 2 minus 10 times the cube root of 2 plus the cube root of 2. So how many cube roots of 2 do I have? -6. Yeah, -6 cube root of 2. Okay, give me 1 to 5. Is that all making sense? Okay. All right, why don't you go try one of those real quick. Okay, so what am I going to do here? The second radical, can I take anything out of that? What about the first one? What should I do on the first one? Okay, say it again.
Get the square root of x cubed.
Okay, so and there's really 2 parts to that, aren't there? I could split this up into, on this first one, I could split this up into the square root of 45 times the square root of x cubed. Square root of 45, what's the biggest perfect square factor of the square root of 45? So 9 and 5. So I'd end up with square root of 9 times square root of 5. Okay, good. How about the square root of x cubed? How do we deal with that? Remember, those are easier. That's x to what power? Did that work? Okay. X to the 3 halves, right? What's 3 halves as a mixed number? 1 1/2, yeah. So what's that tell me? 1 outside and a 1 inside, right? Inside my square root. Okay. So it looks like, I mean, they did this is they combined those into one thing, right? This is the stuff that's going to come out, and that's the stuff that stays in. I like our method a little bit better. So we got, this gave us a 3 outside and a 5 inside, and this gave us an x outside and an x inside, right? Make sense? So let's do this. So this is an x and that's an x, right? There's an outside x and an inside x and an outside 3 and an inside 5. Okay. And now we do have some like radicals. I have square roots of 5x, right? So I've got 9x times the square root of 5x plus x times the square root of 5x. So how many square roots of 5x do we have? Did that not work? Yeah, lowercase hc. Didn't work. All right, so how many do I get then? How many square roots of 5x do I get? I get 9x of those plus x of those, which is how many? 10x, yeah. And a good way to think about that is, I've got 2 terms. The common factor that I could factor out would be a square root of 5x, which leaves behind 9x plus x, right? So I end up with a product of the factors 10x times the square root of 5x, okay? What about that? Got some options here, right? I could simplify the top and the bottom separately. Any other ideas that might be a little more efficient? Yeah, I could put it all under one radical, couldn't I? And then try to simplify that radicand. Yeah, what if I did that? That's not a bad idea, right? What do I get when I divide a to the 7th by a cubed? A to the 4th. And b to the 6th divided by b squared? Yeah. Okay, that helps. And I could split that up if I wanted to into separate radicals, right? I could break that into the square root of a to the 4th, which is what? A squared, and the square root of b to the 4th? Got it. We're done. Okay. What about multiplying? Multiplying expressions involving radicals, nothing changes. The only difference is you're going to have to multiply some radicals, but big deal. So what would I do here to simplify, to expand this out? Distribute. Square root of 5 times 6, can't do anything with that, can I? I've got a 6 outside and a 5 inside, and I'm stuck, okay, with that. Okay, now what could I do when I multiply square root of 5 by square root of 50? I mean, I could combine those into one big radical, which is what the book did. I frequently disagree with the book. I don't think that's a good idea. Actually, I guess they didn't. They kept it as 5 times 50. That's a little better. I don't want to make that a 250 because think why. Like if I make that a 250, a square root of 250, what am I going to do? If I told you guys to go to the board and simplify the square root of 250, the very first thing you would do is you'd draw a factor tree for that, wouldn't you? And what would you get? 5 and 50, and then you'd go from there, wouldn't you? Right? So why would we combine it into a 250 when it's already split? I could turn that 50 into a square root of 25 times 2, and then now I've got a perfect square, right? I've got a couple of 5s that I can take out front, and then I end up with a single 2 and a single 5 that are stuck inside. Does that make sense? Okay. So that's going to give us what then? 6 radical 5 plus 5 radical 10. Can I combine those? Yeah, those are not like radicals, so I'm stuck. But I did make it simpler at least, right? Okay, what would I do here? I mean, you know that pattern. What would I do? What would you distribute first? Square root of 11? What's that going to give me? Square root of 11 times square root of 3 is square root of 33. Square root of 11 times 2? 2 square root of 11, right? Okay. Square root of, or negative square root of 7 times 3, and then I'll distribute it there. What's negative square root of 3, or negative square root of 7 times square root of 3? Okay, everybody get that? Okay. And then finally, negative square root of 7 times 2? Yeah, the 2 is an outside number, isn't it? Okay. Can I combine any of those? None of those are like radicals, are they? I'm stuck with 4 separate terms, yeah. Okay, what about this? Distribute the exponent? Okay, but remember, we're about to take a test over this stuff. If I have something like a plus b squared. Can I distribute the exponent there? I can't, can I? And you guys were pretty good at this earlier in the year, but we haven't used it in a while. You gotten a little rusty. Earlier in the year, if we talked about this, and if I would have said something like, when can you distribute an exponent? You would have said, when you multiply or divide, Mr. Roya. When can you not distribute an exponent? When you add or subtract, right? Remember, that's the case. A plus b quantity squared really means a plus b times a plus b, right? And so we'd have to FOIL that out. I don't want you foiling it out though. At this level, at the honors level, you guys need to just know the patterns, because it's, in this case, it's not that different. But if you're doing a pattern for like a plus b cubed, that's a bit of a process to multiply out a plus b times a plus b times a plus b, right? So we want to be able to just use a quick, simple pattern. What is the pattern for expanding a plus b quantity squared?
A squared.
Plus 2ab plus b squared. Okay, let's get all these real quick while we're at it. The quantity a minus b squared. Plus b squared. Okay, good. How about the quantity a plus b cubed? A cubed plus 3a squared b. No. Plus ab squared plus b cubed. Okay. A minus b cubed. Minus 3a squared b. Good. So the bottom one's the trickiest. How do you know where to put the minus as well? Because it's the same thing as saying a plus negative b cubed, right? And every place where the b is to an odd power, that would give you a negative term. Okay? That makes sense? So you got to know those. So we'll use the a plus b squared pattern here, won't we? We'll just do that. My a is the radical, my b is 6. So what is the radical square root of x minus 2 squared? If you square a square root, what do? Cancel the radical, right? Good, so we're going to get x minus 2. How about here? I get 2 times a times b. What's that simplify to? I'm multiplying 3 factors there, aren't I? 2 times the square root times 6. I can multiply those in any order I want to, though. So we always are going to choose to multiply the outside numbers together separately and then the inside numbers together if we have a case like that. So the 2 times the 6 just becomes a 12 outside, right? And then finally 6 squared is 36. Okay, good. And so that's what we get. We could combine, all we can do now is combine the constants, right? The negative 2 and the 36 just combine to a 34. Okay, make sense?